You know, we rely on equations for pretty much everything, from guiding a satellite through space to predicting the next big thing on the stock market. But how do we know we can actually trust those equations? What if they're wrong? Well, today we're digging into how mathematicians make sure their predictions are built on solid ground.
I mean, let's be real. We all crave a little certainty about what's coming next. It's just human nature. But if you're an engineer or a scientist, a little certainty just doesn't cut it. When the future you're trying to predict is described by an equation, your answer has to be absolutely rock solid.
Just think about what's at stake here. You're plotting a satellite's course. You need to know exactly where it's going. You can't have your equation suddenly throw up its hands and say, no solution here. Or even worse, what if it gave you 2 or 3 possible locations? The same goes for financial models or tracking a pandemic. Uncertainty isn't just an inconvenience, it can be a total disaster.
So how do the pros avoid that kind of chaos? Well, it turns out they have this amazing mathematical tool. Think of it like a rulebook or a quality control checklist. It lets them vet an equation for reliability before they even try to solve it. It's their way of guaranteeing a certain future.
Okay, it's called the existence and uniqueness theorem. Yeah, it's a bit of a mouthful, I know. But what it does is actually pretty simple. It takes a look at any equation that describes change over time, like how fast something is moving, and it asks 2 absolutely critical questions. Number 1, does a solution even exist? And number 2, if it does, is it the only one?
To answer those questions, the theorem runs 2 key tests. The first one is all about smoothness. It's just making sure the path forward doesn't have any crazy sudden jumps, like teleporting from one spot to another. Simple enough. But the second test, predictability, that's the real game changer. It makes sure the path doesn't become so wildly unstable that the tiniest nudge could send it flying off in 2 completely different directions. If an equation passes both of these tests, boom, you've got a guaranteed single future.
All right, so let's see this rulebook in action, because sometimes it can help us crack problems that look completely impossible at first glance.
So take a look at this problem. It seems pretty straightforward, right? We have an equation for the rate of change, and we have a clear starting point. At time 0, our value is -1. Now, let's try to solve this thing the normal way.
And we hit a wall. A huge one. The standard method would involve some algebra where you'd have to divide by 1 plus y, but wait, our starting value for y is -1. So that means we'd be dividing by 0, which is a big no-no in math. The normal approach completely breaks down, but the existence and uniqueness theorem, it doesn't even flinch. It runs its checks and basically says, hey, don't sweat it. I guarantee you a single unique solution definitely exists right here.
And that guarantee makes all the difference. Because we know an answer is there. It forces us to look beyond that algebraic trap. And what we find is the solution is incredibly simple. The value just stays at -1 forever. It's just a flat line. The theorem pointed us to a solution where our usual methods just saw a dead end. Pretty cool, right?
But the theorem's power doesn't stop there. It does more than just give a thumbs up or thumbs down. It actually draws us a map, and on that map, it marks out the exact area where our predictions are guaranteed to be safe.
So this is a really crucial point. The theorem doesn't just say, yep, a solution exists. Good luck finding it. No, it gives you a specific window of time, a safe zone, right around your starting point. And within that zone, it makes a promise. Your unique solution is in there, and it's behaving exactly as it should. Now, take a look at a gnarly equation like this one. Trying to solve it directly would be a total headache. But we don't have to. We can just apply our theorem and, without doing all that heavy lifting, it tells us 3 things. 1, a unique solution exists. 2, it calculates the exact size of that safe zone for us. And 3, it guarantees how the solution will behave inside that zone. It's like having a map of the territory, even if we can't see the path itself.
So at this point, this theorem sounds kind of like a mathematical superpower. And it is, but it also has a really surprising limitation, a blind spot that completely changes how we think about its guarantee.
Okay, check this out. Here's an equation that's simple enough that we can actually find the exact answer ourselves. But before we do that, let's put our powerful theorem to the test. We start with a value of 2. What kind of guarantee is it going to give us?
And here's the twist. The theorem does its thing, and it gives us an ironclad guarantee, but only for this tiny little slice of time, an interval of just 1/8. But when we actually solve the equation, we find the real solution exists on a much bigger interval,
all the way from negative infinity up to 1/2. So what gives? Why was the theorem's safe zone so small and cautious?
This huge difference reveals the true nature of the theorem. And this quote from our source material says it all. The most important word here? Local.
So what does local mean here? Well, it means the theorem's guarantee is absolute, 100% certain, but it might only apply to the immediate future. Think of it like a flashlight in the dark. It perfectly illuminates the ground right at your feet, but it doesn't show you the entire journey ahead. It guarantees the next few steps, but not the whole map.
So, how do we wrap our heads around this? Is a local guarantee a weakness, or is that the whole point?
Let's put all the pieces together. Look at the ingredients. Basic smoothness, or continuity, is enough to promise that a future exists. But there could be many possible futures. It's that second ingredient, that predictability rule. That's the secret sauce. That's what collapses all those possibilities down to one single unique path, even if it's only for the neighborhood right around you.
So the main takeaway is this. That predictability condition is the magic ingredient. It's the difference between a world with infinite possible outcomes and a world where you know for certain what's going to happen next.
And that really brings us to our final thought. At first, hearing the guarantee is only local might feel like a limitation, but think about it. In a world that is so often chaotic and uncertain, where might knowing something for absolute certain, even if it's just the very next step, be the only superpower that really matters?